Hey, let's talk about one of the strangest ideas in physics. You know black holes, right? Those cosmic monsters that trap everything, even light, once it gets too close. Well, what if I told you that the math behind black holes also predicts something just as bizarre, but in reverse? I'm talking about white holes. Now, here's the catch. White holes aren't proven to exist. In fact, most scientists think they probably don't. But the equations of general relativity, the same ones that gave us black holes, say they could exist. So the question is, are white holes just math tricks, or could they be out there waiting to surprise us? Let's break it down. Think of a black hole as a one-way door into oblivion. Once you cross its event horizon, you're never coming back. A white hole is like the flipped version. Nothing can ever enter it, but matter and energy can blast out of it. Imagine a cosmic fountain. Instead of sucking things in, it constantly spits stuff out. In theory, a white hole is a region of space-time where time runs backward compared to a black hole. While a black hole's singularity sits in the future, a white hole's singularity sits in the past. That means, in a sense, a white hole looks like a black hole that's rewound. This isn't science fiction. It comes straight from Einstein's equations. When you solve them for a simple, non-spinning, uncharged black hole, you get what's called the Schwarzschild solution. But here's the twist. The complete solution doesn't just describe a black hole. It also contains a mirror image, a white hole. In these models, the black hole and white hole are connected through something like a wormhole, known as an Einstein-Rosen bridge. Think of it as a tunnel linking two universes, with the black hole as the entrance and the white hole as the exit. Cool, right? At least on paper. But math isn't always the same as physical reality. By the way, if you're enjoying this dive into cosmic mysteries, make sure to hit that subscribe button. We explore the strangest space matters every week, and you don't want to miss what's coming next. So why don't most physicists believe in white holes? First, they break one of the most important rules of physics, the second law of thermodynamics. This law basically says that entropy, or disorder, always increases. It's why an ice cube melts into water but never refreezes itself in your glass. A white hole would lower entropy by spitting out neat, organized matter from nowhere. That's like watching shattered glass magically reassemble itself on the floor. Physics just doesn't work that way. At least, not as we understand it. Second, there's the problem of formation. We know how black holes form, when massive stars collapse under their own gravity. But how would a white hole form? There's no known physical process to create one. If they exist, they'd have to be primordial, meaning they were part of the universe's initial conditions at the Big Bang. And third, they'd be unstable. The equations suggest that if even a tiny speck of matter tried to fall into a white hole, it would instantly collapse into a black hole. So even if white holes popped up at the birth of the universe, they probably wouldn't have lasted very long. Now, here's where things get interesting. Even though they're considered unlikely, physicists keep white holes in the conversation because they could help answer some big questions. For example, take the black hole information paradox. Black holes slowly evaporate over time through Hawking radiation. But if they disappear completely, what happens to all the information that fell inside? Quantum mechanics says information can't just vanish. One idea is that, at the very end of a black hole's life, instead of vanishing, it could bounce into a white hole. The white hole would then release all the trapped matter and information back into the universe. It would be like a cosmic recycling system, swallowing information as a black hole and spitting it back out as a white hole. This idea comes from loop quantum gravity, a theory that tries to merge quantum mechanics with relativity. According to this theory, black holes don't just end in nothingness, they tunnel into white holes. Here's an even wilder thought. What if our whole universe is the inside of a white hole? Think about it. The Big Bang was a singularity in the past from which everything exploded outward. A white hole is, by definition, a singularity in the past that ejects matter and energy. The similarities are striking. Some physicists have suggested that maybe the Big Bang itself was the ultimate white hole explosion. If that's true, then every galaxy, star, and person, including you and me, would be the stuff that got ejected. Our entire universe could be the result of a cosmic bounce, maybe even triggered by a black hole in another universe collapsing. That's not proven, of course, but it's one of those mind-bending ideas that keeps scientists up at night. So far, no one has directly observed a white hole. Black holes, on the other hand, have been detected in multiple ways, through the movement of stars, radiation from their surroundings, and even a direct image of their shadow. White holes? Nothing like that. There was one strange event in 2006. A gamma-ray burst detected 1.6 billion light-years away. It didn't fit the usual patterns of a black hole or a neutron-star merger. Some speculated it could have been a white hole briefly appearing. but the idea never caught on. Most scientists remain skeptical. In short, no smoking gun. Another fun what if. What would happen if a black hole and a white hole collided? The math suggests the black hole would probably swallow the white hole. End of story. But if their masses were equal, quantum mechanics might get involved, creating something weird and unpredictable. And then there's the idea of wormholes, tunnels through space-time linking black holes to white holes. If stable wormholes existed, they could allow for travel across space or even time. But stability is the problem. The wormholes predicted by relativity collapse too fast for anything to pass through. You'd need exotic matter with negative energy to keep them open, and that's something we've never seen in nature. Alright, let's answer the big question. Do white holes actually exist? Right now, the best answer is probably not. At least not in the way we think of black holes existing. There's no evidence, no formation mechanism, and they clash with fundamental laws of physics. But here's the twist. A century ago, black holes were in the exact same boat. They were just math scribbles, and most scientists didn't think they were real. Now we know billions of them exist across the universe. So, while white holes may sound impossible today, we can't rule them out forever. Physics is full of surprises. At the end of the day, white holes are a reminder of how weird and wonderful the universe is. Even if they don't exist physically, they push us to question what's possible, what's real, and how much of the cosmos we still don't understand. Could they explain how black holes die? Could they solve the information paradox? Could they even explain the Big Bang itself? For now, the answer is maybe, or maybe not. But that's the beauty of science. We keep asking questions until the universe gives us answers. So, do white holes actually exist? The jury's still out. But if they do, they might just change everything we think we know about space, time, and reality itself. If you liked our video, go ahead and subscribe. That way, you'll always be first to know when we uncover more of the universe's secrets.